In this example, we have a tube, a concentric tube, basically. In one tube, in inner tube, we have water flowing in, and we have hot gases that are flowing in the annulus part of the concentric tube. The difference between this problem and the ones that we've done before is that now we actually have fins on one side of the heat exchange area. Here, the gas side, not only is the annulus side of the concentric tube, but also we have fins, and now we want to take care of the fin areas and basically see how these fin areas impact the overall heat transfer coefficient for the heat exchanger. What we are going to calculate here is the heat transfer rate per unit length of the heat recovery device. This is basically a heat recovery device, or in other words, you have hot gases that are flowing out of whatever system that you have. They're hot, and you want to recover the heat in the hot gases by running some water in this heat exchanger so that you pick up some of that heat, and then hopefully that warm water will be used somewhere. Everything about the sizing of the tube is given to you. The actual length of the heat recovery device, or in other words, the actual length of the heat exchanger, is not known to us. So we have to do all our calculation assuming that that length is either 1, that is doing everything per unit length, or just keep the L, the length that we don't have, as unknown in all our calculations as much as possible. One note here, there's on the lower right side of the slide, you see that the different diameters, the diameter of the inner tube, inner side of the tube, and then the diameter of the outer side of the inner tube, and then the diameter of the outer tube are all given to you. There's also this T value given to you, which is the thickness of the fins on the outer side. There's also one L value given to you. This length, this is fin radial length that's given to you. This is not the length of the actual device. So from now on, I can't use L as the length of the tube because I've already used the symbol for the length of the fin. So I'm going to use L prime as the length of the actual heat exchanger. So we're going to be, in some relations, you're going to see an L value, and in some relations, you're going to see an L prime value. In both these cases, you have to be clear which one is the length of the fin and which one is the length of the heat exchanger itself. The schematic summarizes our givens. The gases run in the outer side at 800 degrees Kelvin. And we have water running into the inner tube at the m dot is given to you, the flow rate 0.161 kilograms per second, and then the temperature of the cooling water is at 300 degrees Kelvin when it actually gets into the heat exchanger. Note here that your T values, it says TMH and TMC. H is for hot, C is for cold, M is, we basically, if you remember from convection heat transfer relations, the temperature at different points in the cross-section of any flow could be different. When we say Tm, what we mean is the mean temperature in that cross-section. So for example, in the inlet of the inlet cross-section of water, it has different temperatures, but then we're going to say that the mean of all those different temperatures is 300 degrees Kelvin. So don't get confused with that M value there. So here, to start the problem, we do look into the water tables in order to get some of the parameters. Those are the properties are listed there. We're using 300 degrees Kelvin as our best guess. We don't really have anything better. You could have guessed some larger temperature because the water at 300 degrees entering the heat exchanger, by the end, it has probably picked up some heat, and it's going to be arriving at some higher temperature. So it would make sense for you to pick a larger temperature also in order to pick the properties from the tables. The reason we haven't actually done that is we have no idea how long this tube is, and without that information, all of our calculations are going to have some degree of error anyway. So we're just sticking with the 300. I mean, I could assume 400 and someone could tell me, well, this is a very short tube. You're not even going to get close to 310. And then I could pick 310, and someone would say that, well, if this is long enough, you may actually arrive at 500 at the end of the heat exchanger, at the exit of the heat exchanger. So because we really have no idea how the average is going to look like, we're just picking up 300 at this point, and we're getting the properties. Hopefully this is close enough to the actual values. Here in this problem, U value is not given to us. We do have some information on the heat transfer coefficient of the gases. We don't have any information about the fins. We also don't have any information about the heat transfer coefficient on the water side. So if I want to calculate the U value for this heat exchanger, which is the very start of any heat exchanger analysis, if U value is not given to you, you would have to start with a relation that was suggested at the beginning of heat exchanger analysis lessons. So we have 1 over UA, which is equal to, depending on what area you're trying to calculate U for, you would have 1 over UA on the cold side or 1 over UA on the hot side. And that should equal to the relation with the 5 terms. The first term would be 1 over efficiency of any fins if they are present on the cold side, heat transfer coefficient on the cold side, and area on the cold side. You can see that we've turned the efficiency equal to 1 because on the cold side, which is our water side, we don't really have any fins to actually include. So there is no overall fin efficiency here. So we're basically neglecting that as being there. We've just removed it. You can see that I've rewritten the relation again in the bottom line, and you can see that that term has now reduced to 1 over HC AC, area of the cold side. The next term and the fourth term are your the effect of fouling on the heat exchanger. Nothing is mentioned here about the heat exchanger being very old or any fouling effect, so we're going to assume that it's not there. So those are set to be 0. Then there's the R value, or the resistance to heat transfer from the water to the gas through the thickness of the tube. This is not still considering the fins. This is just the tube that has a thickness. You can see on the top right of this slide that we do have a diameter on the inner side, the water side, and we have a diameter on the outer side, which is the gas side, just before the fin is starting. You can see that when that difference is given to you, and a lot of times when the conductivity is not large enough, we do assume that that's there. For now, we're going to assume that it's there unless we realize that it's very small. So that's your RW, or resistance of the wall of the tube. And then the last term is, this term is very general. In case you have fins, you do have to include the overall efficiency of the fins on the hot side, the heat transfer coefficient H of the hot side, as if the fins were not there, and the A, or area of the hot side. All of these are here. We do have fins on the hot side, and we do have some flow of gas, which for that we know the H is 100 watts per square meter Kelvin. That's on the top of the slide. So we do have that information, some of that information. Now, if we are looking at this relation, you can see here that I've put in red UA is equal to 23.6 L. We don't know this yet. This problem is basically starts with listing everything here, and then you do list everything in the bottom after you find those out. So what I've done here is I've first set up my relation, and then in the next few slides I'm going to show you how we figure out the H value on the cold side to become 1883. So for now, let's say that we figured out through some internal forced convection analysis that this H value is 1883. You would substitute it here. Your area on the cold side would be your pi, and then the diameter of this cold side, which is 24 millimeters, which is 0.024. And then L prime is the length, or the assumed length of the tube. We don't know the length yet. So that's how I would set up my first term. The second term, or number 2 there, is the resistance through the wall of the tube. And that one, again, I do have the relation there. I will be able to calculate that and to show you how I've got 7.1 by 10 to the negative 4 divided by L prime. But for now, when I actually get to those calculations, you will know that I'll have to put it in here to basically calculate the UA. The last term, or part 3, I'm calculating my overall efficiency of the fins to be 0.931. Again, I'll show you how I've got that. That's some calculations. And the H on that side is already given to me. That's 100. That goes into that the bottom right side. And then there's also the area of the hot side, which I calculated to be 0.31 L prime. Again, This area of the hot side is basically the area, the total area of the hot side. That is the base and the area of the fins all together. As soon as you put in that overall efficiency for the fins, you do have to consider the area on the hot side as well, which has some calculations related to it. So we will be able to calculate a couple of things. One is the heat transfer coefficient HC on the cold side that we are going to calculate as 1883. We're also going to calculate what the resistance for the tube wall is, and we're also going to calculate the total area on the hot gases and the overall heat transfer coefficient on the hot gases. All of these I'm going to show in the next slide how we calculate, but once we do calculate them, we are going to find out what UA is for our heat exchanger, and that's the beginning of now dealing with heat exchange calculations. So let's go to the next few slides to see how we actually got this 23.6 L value. Now in this slide, we're just focusing on the water side. This is internal forced convection. This is water flow into a tube, and we know that in order to calculate that the H value for this, we do need to calculate first the Reynolds to see what type of flow we have. In this case, we are having a Reynolds number calculated as 1990, which is bigger than 2300, so we decide that this is a turbulent flow. There's two relations for turbulent flows. The Nusselt number relations is 0.023 Reynolds to the power 4/5, Prandtl to the power n. And this n value, we do need to know if we are heating the flow or if we're cooling the flow. In our case, let's explain it another way, if the surface temperature, the tube temperature, is it actually smaller than the water temperature, or is it higher than the water temperature? In our case, the tube is actually warming up the water. It's the gases are flowing outside of that tube and making that tube very hot. And as a result, I do expect the wall temperature to be higher than the temperature of the actual water. So that's why I will pick n as 0.4, because I assume that that tube is hotter. So that's my Nusselt number relation that's set up. It basically requires my Reynolds and Prandtl to go in, and on the left-hand side, Nusselt is broken down to heat transfer coefficient, diameter, and K value, which is the conductivity of the water that flows in. So you substitute the diameter and the conductivity of the water as 0.024 and 0.613, and you substitute everything else, the Reynolds and the Prandtl, and you should be able to get H value as 1883 watts per square meter Kelvin. This H value goes into the first relations that I showed you. I told you that I'm going to calculate this H value as 1883, and I'm going to bring it back to calculate my UA, and this is basically how I got that H value. Another thing that I needed to calculate was the resistance of the tube wall. So here we're calculating the thickness of the tube between the water and the gas, the tube that's basically having the water flowing in it. This is our typical resistance relation, ln of the diameter of the outer side of this tube divided by diameter of the inner side, divided by 2 pi conductivity of the tube, and multiplied by the length of the entire radial system that you have, which in this case is the length of the heat exchanger, which we don't actually know. So we're calling that L prime. We're not calling that L because we've already used up that symbol for the length of the fins that are on the outer side, on the gas side of this heat exchanger. So once you actually substitute the values for the diameters, you will be able to arrive at 7.1 to 10 to the negative 4 divided by L prime. Again, we don't really know what the length of this heat exchanger is, and at the end in our calculations we won't even need it, but for now I'm just keeping it there because later it's going to cancel out. In this slide we're calculating the overall efficiency for the fins on the gas side. So in order to calculate overall efficiency for fins, I have listed the formula that you would use in order to calculate overall efficiency. It's 1 minus AF, which is area of the fins, divided by AT, which is total area. Total area is area of base plus area of fins. And 1 minus efficiency and the subscript here is F, the efficiency of one single fin as opposed to the efficiency of all the fins together. So you would have to start with calculating efficiency of a single fin. Once you calculate that, you substitute it in this relation. How do we actually get that? All the right-hand side calculations are basically helping us calculate the efficiency of the fin. In order to do that, you do need to use the relation tan hyperbolic ml divided by ml, and that basically, the m has a definition. So in order for you to calculate m, you do need the H, or heat transfer coefficient, on the gas side, if there were no fins. You also need to have the conductivity of the fins that you're using, the thickness of the fins, and that goes, that basically is giving you the formula for the M. We do know all that information. So you are able to calculate the M value, which you then substitute in the relation. Again, this relation comes from your book, from the way these fins are shaped. You do substitute this in the relation, and you are able to get the efficiency of the fins based on the M and the length that you have here. Now, once we actually substitute the length that shows in this formula, this is the length of the fin. So you do have to be careful that this is not the length of the entire heat exchanger in this case. So once you calculate the efficiency of the fin, you are able to get a 0.911 value that goes into your original top left side relation. So this is how you will be able to actually calculate the overall efficiency. Now, in order for me to calculate the overall efficiency, it's not just the efficiency of the fin that I have to calculate. I also have to get area for the fins and total area. Those I'll do in the next slide. In order for me to calculate area for the fins, I do need to understand how the shape is. Take a look on the top right or middle right of the screen. I have tried to draw on how these fins look like. You do have, let's say, an L prime length fin and the L as the height of the fin. And the area on one side of the fin would be L multiplied by L prime. Of course, every fin has two sides, so you would have to multiply that by 2, and depending on how many fins we have, you would, like n fins, for example, your area for every fin would be 2n L prime. That's how we actually come up with the areas. You do have to make up your own formula for calculating areas. It's basically looking into how the fins look like and seeing how we can actually get the areas. So once you calculate that, of course, we don't know the length of the fin. We don't know the length of the entire heat exchanger, so we don't know L prime. And because we don't know that, we are going to calculate all of this as a function of L prime. So it's going to be 0.24 L prime. Then we go calculate the area of the base, which is, well, some of the base is already covered by your fins. So it's not just pi d L prime, that's the area of your base necessarily. You do have to do pi d L prime and then take out the parts of the base that the fins are covering. How many fins are covering that? That's n fins. Every one of the fins has thickness t, and the area that is covering the base will be TL prime. So you will have to take that out, and that's how we get the formula for AB, which is area of the base. It's pi dl prime, which is the total area on the outer side of the tube, minus NTL prime, which is the area that the fins are taking. That will leave you with the area, the exposed based area, which again is a relation in terms of L prime, because we don't quite know what the length of the heat exchanger is. And then we can add these two up to calculate the total area, which will add up to be 0.31 L prime. Again, this relation is based on L prime. So now in the relation that we were working with in the previous slide, we got our fin efficiency, single fin efficiency, but we also needed area of the fin divided by total area. This together will become like, divide those two together, and you should be able to arrive at 0.77. The L primes cancel out at this point. So you are able to actually substitute that in your overall fin efficiency relation, and you should be able to get 0.931 as the overall efficiency of the fins. Now that we're done with the calculation of overall efficiency of the fins, there's not much left for us to calculate. Based on all the calculations so far, we have calculated the UA to become 23.6 L prime. That's the overall heat transfer coefficient on the hot side, area on the hot side, and we've basically just calculated this. I mean, it could be hot side or cold side. We haven't used any areas yet. If I pick, for example, area of the cold side, then I'll be able to calculate U for the cold side. If I pick area of the hot side and substitute it in here, I'll be able to calculate U for the hot side. But I don't even need to do any of that. If I want to calculate in this problem the heat flow rate per unit length, or if I want to calculate the heat flow rate over the entire length of the heat exchanger, I need to calculate UA and temperature of the hot fluid minus temperature of the cold fluid. That's all I need. I don't really need to break down the UA to the area and the U. I've already calculated the combination. So that's why in the formula here you have Q equal to UA cold or hot multiplied by TH minus TC. So UA, doesn't matter which one you pick, it has to arrive at 23.6 L prime, and I substitute that. But then pay attention to how we're calculating the mean difference between the temperatures of the hot gases and the water. This is a particular type of problem. We have no information about the length of the tube, and that's why we're going to assume everything on the inlets. This is not quite accurate, but we have to do this because we don't know what the length of this heat exchanger is. We don't know what the outlet temperatures are, so there's no way we can use, for example, logarithmic mean temperature method or any method to figure out what the mean temperature for the hot gases are, what the mean temperature for the water is over the length of the tube to be able to calculate this heat flow rate. That's why we're going to make an assumption by saying that hot temperature or the temperature of the hot gases is 800, and the temperature of the water, we're going to just take the inlet temperature. Again, this is not suggested method for every other heat exchanger analysis. We only do this because we have no better information. So we put our UA there, we put our temperature difference at the entrance, and we arrive at heat flow rate to be 11,800 L prime watts. Of course, the problem is not asking me to calculate the total heat flow rate for a heat exchanger that I don't know its length. I am supposed to calculate heat flow rate per unit length of the heat exchanger, so I have to divide this Q by L prime anyways, and that cancels that L prime at the end. So I'll basically use this 11,800 L prime, and I divide it by L prime to calculate heat transfer per unit length of this heat exchanger, and that should arrive at 11,800 watts per meter. You can see how my not forgetting about the L prime is now helping me to actually cancel it out. You couldn't have assumed that it's not there. The length of the heat exchanger shows up in every part of your calculations. Sometimes it will cancel out, sometimes it will not, but you will have to keep it until this very end. And the only thing that you can say for sure is the heat flow rate per unit length of the heat exchanger. And once you do have any length, you should just multiply this value by that length.